It doesn't talk to me. The other one's always talking to me. So we talked about the number of degrees of freedom. So first of all, what did we say a degree of freedom is?
Independent motion.
Yeah, it's going to be some independent coordinate or something that you're going to need to specify the motion of a particle. And the key word is that it has to be independent. And so we said if we have 4 particles moving in 2 dimensions, imagine I have like 4 particles here. They're independent and they're moving on the board. How many degrees of freedom would I have then?
8.
Yeah, because I could have an X and Y for each particle. I could have 2. I have 4 particles, so 2 times 4 would be 8. Now, let's say I now have the particles are now paired. So I have, 1, 2, 3, 4, and they're like this. Okay. How many degrees of freedom would I have now? They're still confined to moving the board. How do you get 6? Yeah, so there's going to be 2 constraints. We're going to assume that this bond length here is going to be fixed. And so what do you do? That the actual number of degrees of freedom. Okay, it's going to be the number of dimensions, in this case 2. It'd be 3 normally, but it'd be 2 in this case because it's moved forward. Okay, times the number of particles, in this case here 4, then minus the number of constraints. This would be number of. So that's what you'd have in this case here. That makes sense? So where this is going to come in, and we're going to make a lot of use out of it later on, but not quite yet, is that what we're going to end up with is something called Phillips constraint theory and then temperature dependent constraint theory. So later, we will develop Phillips constraint. The Philip. Okay, he has stuff doubled in his name, and I don't honestly know what gets doubled in his name. Maybe the L, maybe the P's. It's something like this. Double every letter. Philip Thorpe constraint theory. Okay, and then later on, this gets modified to what's called temperature dependent constraint theory. And Philip, it was initially Philip's idea, then I think Thorpe realized there was a mistake and corrected it. Probably shouldn't say this for this being recorded. I've heard Phillips talk a number of times. He's utterly incoherent. He's a very nice man. But I can honestly say I have no idea about any of his. I listen to his talks and go, huh? And then I read his papers and I go, huh? But John actually is worth it. He's top notch. And John is infinitely smarter than I am. I defer to him, but I honestly do not understand anything the man says in every talks. I do not get it. That's just me. So the idea is here is that let's say we had n particles in 3 dimensions. So how many particles? How many degrees of freedom would we have? 3n. Now what we can do, we can start putting. Let's say now they're forming a glass network, and so if they're forming a glass network, you're going to have constraints. And what kind of constraints can you have? Well, I can say that this atom here is going to form a bond with this atom over here. So what I can do is I can have a linear bond constraint. So I can specify a certain number of linear bond constraints. But then what I can do is if I have another part, and they're called alpha, the number of linear bond constraints. But then if I have a particle here and a particle here and a particle here, I would have 2 linear bond constraints. But then also, if I think of these as being like balls and sticks, I can also have an angle between the 2 like this. So there would also be an angular constraint as well. And so I'd have linear bond constraints, and then I'd have angular constraints. And you look at this. And their idea is this, is that what would make a good glass form? And so they argue that basically that if you had a lot of degrees of freedom in a system and not a lot of constraints, what would happen? That'd be a very sloshy system. The word we'll have is floppy, but we don't have that yet. Be a very floppy system, and you can imagine that that system would kind of move all over in such a way that it's going to crystallize real easy. So that wouldn't make a good glass because it's crystallizing too easy. But then maybe you have another system where there's a whole bunch of constraints on it. If there's a whole bunch of constraints, you'd also expect that one to basically form a crystal as well. So that'd be an over-constraint theory. And so their argument is that basically an optimal or a good glass former is going to be the case where the number of degrees of freedom and the number of constraints are going to be equal. And that it seems to actually work, actually have some profound. And then what happened here, and this was actually done by Gupta, and then John here. What they did, it's like really quite elegant. What they're going to say is that as you have a system that's really, really high in temperature, you'd have no constraints. You'd have 3 end particles. But as you start cooling it, what can happen that different types of linear bond constraints can set in different constraints. And so as the temperature cools, you're going to have different constraints coming in. And what's going to happen is that you can actually then start figuring out kind of how the system's going to evolve as the temperature is cooled. And they get a lot of mileage out of this. And so you're going to start being able to predict things based on the composition of the glass. So they're going to actually see how fragility can change, which I find out, glass transition temperature can change, all based on composition. So they're going to get a lot of mileage out of this. But it just comes down to really counting degrees of freedom. And as I told you, counting is not the easiest thing that comes to me. So to me, when I look at these systems and say, okay, now, how many linear bond constraints do we have? 1, 2, and it comes very hard. It's at least counting is not an easy thing. Okay, that makes sense?
What did you mean, different constraints?
So in other words, you could have, okay, so here you could have linear bond constraints. But now let's say you start having different atoms. Okay, so maybe this is boron and this is oxygen. And this, so, well, you can have those different bonds coming in at different temperatures, linear bond constraints. But then also you could then maybe start having then van der Waals interactions between things. You could start putting in different interactions. And then also different angular bond constraints, all coming into different temperatures. And so that allows you to do a lot more. And we'll set this all up. And we'll work on a number of cases. You do have to know about the structure of the system. If you don't know about the structure of the system, you can't apply this method. If you don't have the structure of the system, this is okay. And let me just say one more thing because about this, and then we'll go on with nice little calculations. Very frequently, what you're going to do when you see things, you're going to see a lot of 3n-6 number of degrees of freedom. You're going to see the number of degrees of freedom. Look at many things you're going to see. You're going to have this thing 3n-6. And I want to explain about this -6. Okay. Well, let's have an outside class instead. We can do it anyway. So let's take okay, so let's say here's my object. Okay. I want to just show you what the number of 6 is. So now eventually what's going to happen if we have 3n particles, they're going to form some sort of glass, some from a system. So imagine here's a system here. Now it turns out there's some degrees of freedom that no matter what we can't, they're kind of always there, but we don't care about them. So let's say if I have the degrees of freedom on something, it should be enough to basically specify exactly where this box is. Now, does it matter whether this box is here, whether this box is here, 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 or whether it's rotated like that? It doesn't.
Doesn't matter for what?
Just if I wanted to describe this box. It would matter if I have the box here, or have the box here, or have the box here. It would not. Also, it would matter whether the box is like this, or the box is like this, or the box is like this. That wouldn't matter. Okay. But what does that mean here? So how many degrees of freedom would there be connected with this type of motion here? In other words, the center mass of the system. There'd be 3 degrees of freedom connected with the center mass of the system. Okay, that's actually 3 of the 6. Now, what can happen too? How many angles can I have for this system? Yeah, I could rotate it this way. Okay, I could rotate it this way. Then I could rotate it this way. So there'd be 3 angles. So when any system you have, the total maximum number might be 3n, but you always subtract 6 because no matter what, you always have an XYZ for the center mass that you don't even care about. And then you always have then 3 more angles like this that you could care less about as well. Okay. Often the angles are called Euler angles. Don't worry about. For those of you who had classical mechanics, you know what an Euler angle is, but they're not really necessary. So basically, this would be the 6 here is coming from the 3 center mass degrees of freedom and the 3 angle orientations for the object. And no matter what, you can never really get rid of that. Okay. Now, usually n is going to be how large for a system?
Larger.
Avogadro's number. So 3 times Avogadro's number minus 6. Okay, what can we do with this 6? I think safely get rid of it. But when you see a lot of calculations, you're going to see this like minus 6 in there, and you're going to say, where on earth is this minus 6 coming from? It's entirely coming from center mass and the rotational part. So the 6 here is the 3 center mass degrees of freedom. The object. The other one is going to be the 3 orientation. That's what they're coming from. And often if you look at a lot of things, the angle, the orientation angles are called the order. Okay. Don't worry about how they're specified. There's a way they're specified, but it doesn't. The main thing is that there's 3 angles. Questions with that? Okay. So now that said, let's actually look at kind of the expectation values we can do. I want to mention a little bit about a correlation function just so you can see how we find it. I'll show you, we'll see later on why it's going to be really, really important because we're going to hit correlation function. It's hard, but toward the end of the class. And then I want to show you when you go to solve these things, what kind of integrals you're going to get because you're going to get something called a gamma function all the time. Okay, so recall. Expectation values. Thermal averages. Given. Okay. So let's say I have some quantity here, A. Doesn't matter what A is. Okay. A is going to be some function then of P and Q. Okay. What does the, okay, maybe I should write it like this. What did I say the P, when I say a P like this, what does it refer to? This P is all the momentum of the part of the system. And the Q I mentioned before, what's the Q? Position. Yeah, the Q, often positions instead of R get replaced by Q. As a classical mechanics reason. Okay. So the Q here refers to the positions. So this is kind of collective notation. This P here refers to all the momentum. And this is all positions. No, we're not going to do that. Okay. It turns out you can actually do things in terms of Hamiltonians, and you frequently do when you actually go to when you start putting quantum mechanics and stuff. But we ain't going to do that. So often, what do we say this A is going to be?
Energy.
Energy. That's a very good one to do. We're going to do one of velocity. I want to show you what happens with velocity. It's going to give rise to a gamma function. Actually, we're going to do velocity squared. Oh. So if I wanted this fellow here, okay, how do we say we do this again? Classically?
Some of the probability of.
Yeah, we have to sum. Normally, what did we have for this? We had, this is what we had before. Right, that's the general one. And what did we say that happens when we do it in terms of classical mechanics? Classical statistical mechanics? Meaning? We have to, this is summing over all possible microstates.
We have to integrate.
And classically, what is all possible microstates? We have to sum over all the momentums of the particles and all the positions of the particles and go from there. So what do we do? We have the sum on D3 P1, D3 P2, all the way here, all of them. Okay. And the same thing on the R's. Again, I'll put R's, but if you look at most textbooks, it's going to be Q. Whatever this A is here. So this A, which would be a function of P1, P2, all the way to Pn, Q1, R1, R2, all the way to Rn here, times. Okay, hold that thought. We need the P. Okay, so then we have this E to the minus beta. Actually, I'm gonna have to go down here. I wouldn't have to do that if I were an Olin at all like that space. Okay. Then what would the energy be?
The potential energy plus kinetic, so that's.
Okay, so I have the P1 squared over 2m. For the first particle, P2 squared over 2m2 for the second particle, all the kinetic energies. And then
Plus V1 plus V2.
all the potential energy for the whole system here. So the potential energy is going to be some V, so that'd be from R1, R2, all the way through to R.
And that's in one dimension.
Okay. Well,
One dimension.
no, this would be an dimension. Because this would be for the whole system.
Yeah.
And this P1, when I'm running like this P1 squared would be what?
Px1 squared plus Py1 squared.
Exactly. So this, just to make that clear, this guy here, this P1 squared, would be P1x squared, P1y squared, P1 with some that. Okay. And then what do we have to do? We have to divide this E by our friend Z. And what is our friend Z? It looks just like this whole mess here.
Except
What doesn't it have?
A.
It doesn't have the A in there. That makes sense? And then that's what we would have. So normally what you do is at the C here, you have the whole thing written again, but without that A. That makes sense? Questions? Now, in principle, what could this A also depend on? Could depend on all the positions, all the momentum, but what else could it be a function of? Be a function of time. So what we'd have here that in principle, by time to time. So I could have this A depending on all the positions, all the momentum, all the positions of T is well like that. So what can happen here is I can make a graph of the average value of A versus time. And what would I have here? Well, this from right here. I don't want to do it like this. I'm just going to say A. This is going to be my average value here. But in general, what might this A look like if I plot it versus time? The average value is going to be fixed, it's constant. But this A might actually kind of like vary like who's like that. Okay, it's going to average over that A. It's going to bounce back and forth along so like that. And along there you can say, well, yeah, that makes sense. You'd expect it sometimes to be high, sometimes low, and on average it's going to be the same thing. Makes sense. But it turns out there's some information here. We sometimes worry about, this peak here, what that peak is, and how long does it take to actually kind of go down there. And so we would like some measure to kind of, look at these like little fluctuations here. And so what we're going to do, we're going to define something called an autocorrelation. So we define an autocorrelation. What it's going to be, it's going to be basically, we're going to look at the A at one point and the A at another point. So I'm going to have some little time here. Look here, this is at some point T. You're going to look at some other little time over here, and I'll call it T prime. So what I'm going to do is I'm going to have this A, I'll just say at T prime, and some A at T, and I'm going to look at the average of that right here. And this is by definition, the auto correlation function. That's going to be connected to a lot of transfer properties. Okay, we haven't really done transfer properties yet. It turns out this is going to be connected with transfer properties. So I just want that, we're not going to do anything with it yet. Just kind of stick it, have it in your notes someplace. I'll refer, toward the end of the semester, I'll refer back to this. But right now, just kind of keep it someplace in the back of your head. Okay?
So it's just an average of the product?
At different times.
Yes. Yeah.
Okay. So in other words, if the T prime equals T, then it's just going to be quantity squared. Okay.
Yeah.
And what we're going to find out is that if this T prime is actually a lot further away from this, it actually just ends up being a product of basically, it just ends up being a quantity squared. Okay. We don't know later. Yep.
Sorry about
Yep.
that, but what is the main reason of me define auto correlation function?
Because we're interested in these fluctuations, we want to see whether they persist. Okay, so if we have the value here at t, and then the time a little bit t prime here, we want to see is it 0? Is it a constant? So it's going to be a measure basically kind of how these little fluctuations here, how long they persist.
No, but how can we be sure about that? Because it's the important what kind of slice you
Yes,
had. So
this is going to be completely variable that we can do. And what we're going to find out, okay, kind of give you give away the game. While this versus t prime, and let's take this to be 0. Okay, what we're going to find out is that up here, this is going to be like the a squared value. So if I'm right, let's say that this is t here. This is t equals t prime. So this is, well, I'll take this to be 0. So let's take t to be 0 here. Okay. So if I'm right here, t prime and t are the same. This is going to be here. We're going to find out later on. We're not there yet. Okay, but if we wait way out here, okay, this value here is going to reduce to basically just a by itself quantity squared. And we're going to see that this thing kind of decays like this. Okay. And so how this thing decays, there's going to be some sort of characteristic time for that. And we're gonna connect it to transport properties and stuff like this. We're not there yet, though. That's going to be the important thing. And plus, when you say correlation function, people just think you're smart. It's one of those things where as soon as you say correlation function, even if every word coming out of your mouth after that is garbage, you said correlation function. And people will probably shut up because they think, wow, you know what a correlation function is. I don't. So you must be smarter than I. Look how far I got. So you can do a lot with this. Okay, okay. It's like the density matrix in quantum mechanics. You mentioned the density matrix in quantum mechanics. It's like, oh no. They use the density matrix in quantum mechanics. All right. That's scary. Okay, questions with this? Okay, so I want to show you kind of a common thing we're going to get and how we're going to go about analyzing these things. So often, very frequently,
It's often or very frequently?
both. Okay. Very frequently, we come across integrals and stat mech in quantum mechanics. And that involved a gamma function. And I want to show you what one is, and I want to show you how to go about dealing. Okay. It's one of those things, once you know how to do them, really work with them, you can crank out really awful looking intervals really, really fast, and people think you're smart. So, again, look how far I got. So, okay, the gamma function. by definition is, and this is one of these things, commit this function to memory because it occurs all the time. Capital gamma, this is the number n, variable n, the integral from 0 to infinity of x to the n minus 1 e to the minus x. That is the fundamental definition of a gamma function. You could say, well, why is that even useful? Well, it's useful because it occurs all the time. That's going to have really nice properties. Okay. So let's go and figure out how to solve this. So how do you go about solving this? What is a physicist's favorite way of solving any integral that you've ever seen? Not a bad guess. Okay. Integration by parts. Okay. So when you come across an integral, you have no clue what to do with in physics. Always try integration by parts first. Okay. Okay, so use integration by parts. So there's something we'll let u equal, something we'll let dv equal, which is which?
U is going to be e minus x.
So u is going to be
X to the n minus
x to the n minus 1. dv is going to be
1. So e to the minus x dx.
e to the minus x dx. So we take du. du is
N minus 1 times x to the n minus 1.
n minus 1. And I'm going to write the, okay, I know it's going to be n minus 2. I'm not going to write it like that. I'm going to write it as n minus 1 minus 1. There's a reason I'm doing this. Yes. And what is v then?
Minus e minus x.
Minus e to the minus x. Then what do? You do this. So we have our integral here. What do we have? We have this times this. So this would be minus x to n minus 1. E to the minus x evaluated from 0 to infinity. Then minus a minus plus integral from 0 to infinity n minus 1 x n minus 1 minus 1 e to the minus x dx. Okay. This side over here, when you put in the upper and lower limit, you do 0. I'll call it the n minus 1. Make it a little obvious what the C's there. This is my gamma. Okay. Hey, why did I write this as x to the n minus 1 minus 1, not x to the n minus 2?
I think that integral looks like a gamma function of n minus 1.
Yes, this is nothing but the original definition of our gamma function. This right here is nothing but the gamma function of the quantity n minus 1. We would take n minus 1, right? Here's our n. Then we subtract 1 from that. So we get this. So you get the important result that gamma of n equals n minus 1 times gamma of n minus 1. Does that make sense? Questions? Now, let's take the case where n is a integer. Okay, so what would we have in that case here? So we have gamma n, then minus 1. It's here. What would a mathematician call this expression?
A recursive definition.
Yeah, this is right here. This is a recursive or recursion relation. Okay, recursion is one of those things too, when you get to it, it's like, oh no. Is a recursion relation. Only smart people understand recursion relations, and it's one of those where it's just
Wonderful.
okay. So what do you do with this? Okay, so what you do, you kind of you use this, you have this relationship here, but then we ask, what is this? Well, it's going to be if I had n minus 1, this is n minus 2, n minus 2. Okay. If I then put the n minus 2 in here, then I have n minus 3, then n minus 3. I can kind of feed this back upon itself. So what I can do is I can use this definition here to put it back into here. This guy is putting in my recursion relation.
N minus 2 times gamma
N minus 2 times gamma, n minus 2. Yes. Hey,
I think you have to keep going.
we keep, and this is all we're going to do for the rest of the semester. We have a lot of blackboard space we're going to do. We're going to start using that space there, raise it here. We're not going to get any further, but we're going to have a lot of terms. And that's the important thing, is that your notebook is going. It looks like you've done something. Do one more time. Okay. So I use a recursion relationship here again. So it's my n minus 3, n minus 3. Well, what did we say? N is a integer. So eventually this is going to go to the gamma of 0. Or let's try with 1.
Let's try 1.
So I can keep on doing this until I get to 1. The question is, what is gamma of 1? Okay, let's just go through and talk about it. According to our definition, gamma of 1 is 0 to infinity of x to the 1 minus 1, right? N minus 1, e to the minus x. X to the 1 minus 1 is x to the 0, so that's 1. This is e to the minus x dx. That integral is minus e to the minus x, evaluate from 0 to infinity, which is, that goes to 1. That makes sense? So what do we have here? We have gamma of n, n minus 1, n minus 2, all the way down to 1. That is frequently called n minus 1, right? Because it's factorial.
Yeah,
So you
makes sense.
have to say it right. Ah.
Oh,
So you're n minus 1 factorial. Okay,
6 degree.
that's good for you. Okay, so let's try an example to show you the beauty of it. So if I had this. What does that have to equal? Without doing any work, because we want to show off. First of all, when you want to show off, you always have to start off with the generic like that, just to kind of emphasize. Okay. Can't wait to find out. Okay. There's going to be 5 factorial over 3 to the 6. Okay. Okay, so let's go through and figure out why. Okay, so if it wasn't for that 3, what would you say this is?
Factorial.
Okay, that was gamma to the,
N minus 1.
but if I just had that, which gamma function would that be?
Gamma of 4.
Gamma 5, gamma 4, gamma
Gamma
6.
6.
Yeah, remember what your gamma function is. x to the n minus one, you did minus x to the x. So this is a 5. That means that this is actually a 6. Okay. That'd be gamma to the 6. Gamma to the 6 then has to be put into a little prescription here.
N minus one.
Nine.
So
5 factorial. So that's what we would have if we just had that. Okay, now the question is, why do we then have to divide this by 3 to the 6?
do we use substitution?
Yeah, this is not the form of a gamma function. It's almost a gamma function. But that 3 is screwing everything up. So what do? We do a u substitution, not a me substitution, not a he or she substitution, or we or they substitution, but a u substitution. Okay. That was then it costs a lot of money. It's expensive. Okay, so we're gonna say let u. What will u equal?
3x.
3x. Frequently called threx. Okay? The technical people call it threx. Okay? Crazy. Okay, so then du is 3dx. Or dx is a third du. What else do we know? We know that x is u over 3. So now we just substitute everything in here. First of all, what would happen to my limits?
Not change.
Absolutely nothing. Right? Nothing happened to the limits. So I get this from 0 to infinity of u over 3. Okay. E to the minus u du over 3. What would this be? This would be 1 over 3 to the 6, which is 1 here, 5 of them from here. 0 to infinity, u to the 5th, e to the minus u du. This is nothing but a
Gamma function.
standard gamma function. That's your gamma to the 6. It's 5 factorial. Okay. So what would this be?
To the minus 10.
So this would be 9 factorial over 4 to the pretty slick. Okay. What happens if we have the following now? Well,
Battle against time continuum.
possible. Well, what happens if I have this? We go, oh no,
It's 1. You can still do it.
that's not a gamma function. How come? An x squared.
But it's an x squared to the first power, so we can do a use of.
U sub. Okay, so what we're going to do, we're going to make this into a gamma function. Okay, using U sub. You're going to let u. What will u equal?
X squared.
4x
For
squared.
sure. For
And then I'm going to say du is 8x
yes.
dx. So what is my buddy x?
Dx degree. Or, no.
I take over my 4, take the square root, so this gives me that x. So square root of q over 4. Everything else pretty easy. Here's the 1/2 over 2. And then I'll put that in here. Dx, my du. And I can solve this in for dx. So dx, this gives me a 4. This will give me a quarter. Du u to the half.
Where are you?
That is, you over 4 you have.
This one here would actually bring it up here like this, so that would actually go. Now, the way we're gonna all do this. Like this. Okay. Makes sense? Let's put it all and see what we get. Okay, so I go from 0 to infinity, my limits don't change. What is my x squared?
2.
No. My x squared is u over 4. Okay. This goes to e to the minus. Tell me about dx. That's my buddy here. Quarter, u to the minus a half, u. Pull out all my constants. So I get 1 over 16, 0 to infinity, I have a u, then I have this guy here, this is u to the 1 half, e to the minus u, du. What is this?
Gamma. 3/2.
Gamma of
3.
3/2. You said that's no good. I mean, I don't know what gamma 3/2 are. All I have is a new symbol. Hey, what do you know about gamma functions? Do they obey anything?
The equal position rate.
No. Okay. The recursion relation. So what do I have? From the recursion relationship, remember? We made no restriction on what n was to them. Okay. So what does that have to equal then? Like this has to be 3/2 minus 1 gamma 3/2 1. Does 3/2 minus 1 have a better name?
Minus 1/2. 1/2.
Okay. It is.
1/2.
Okay. So we have 16. We have a half here. There's gamma of a half. Hey, have any of you ever calculated maybe recently gamma of a half? Maybe say in homework 2. Okay. The square root of pi. So what are you left with? We're left with 1 over 32 square root of pi. Okay, those integrals occur all over the place in stat mech, occur all over the place in quantum mechanics. That makes sense? Not the most exciting thing, but it's something you have to do to calculate. So let's try an example here. So you can see where they really limit this.
You're good. Keep going. 5 more minutes.
Consider one particle, one dimension. I want you to find the x squared. Right there, we found it. We're done.
We have to integrate or roll into all positions.
Yeah, let's just go through and set it up. What would it be? So what would it be? You have to integrate over all momentum. In this case, the only momentum is
The exponent.
the x momentum. So to have an integral minus infinity to infinity of dpx. There's nothing else to integrate over. Now we have to integrate overall position, which would be
DX, just
the integral dx. I'm not going to put minus infinity to infinity because I'm assuming my particle's in a box. Hey, what do you think the length of our box will be?
L.
L. That's going to be a good name for it. L. What else do we do? We put the Vx squared in here.
X squared,
Times our e to the minus,
potential plus beta.
which is what in this case?
I mean, e to the minus beta, right? So
Okay, so we're going to have a minus beta times
P squared over to
px squared over 2m plus our potential, which is 0 because there's just one particle here. And then we have to divide this by basically the exact same thing without
the V squared.
the Vx squared in there. That makes sense? Again, why don't we have to worry about that? I told you before, there's that factor of h coming in. Why don't we have to worry about that factor of h?
It cancels out from the partition.
Yeah, you would have it divided by h in here, divided by h in here, those h's cancel out, so you just have this nice little diagram. Okay, let's calculate this
I think you forget the bounds on the position.
on purpose, because I was just, we're gonna assume that it's overall. You can go from 0 to L, but I'm just gonna leave it generically and say it goes to L. Okay, so you tell me what to do. You are in control.
So there's no x dependence in the function, so we can factor it.
Okay, so I can rewrite that and saying, and what am I going to do from the minus infinity to infinity, Trevor? Yeah, that's going to be an even function, although I'm not seeing a p in here.
It's e to the px squared.
Yeah, but this is a b. Okay, engineers and physics majors. What is linear momentum p?
It's
Thank you. Okay. And much of that gets you some back to Siberia.
Yeah.
That's it.
An extra square on that.
So px then going to be your mx. Right? So I can multiply top and bottom here by m squared and I can put a p into it instead. Okay. So what I'll do is I'll pull out the 1 over m squared. And then I have an integral of 2 in here. From 0 to infinity. Of then dpx x squared e to the minus beta.
You're also gonna have the two. The
Yeah,
two is
I mean, it's all gonna go away, but I'm gonna make it explicit initially. Px squared over 2 out here. And this integral dx, and then this part here is just gonna come our length of the box L. And this whole thing here then gets divided by integral from 0 to infinity. You did the px, e to the minus beta dx, integral dx, that is L. So the 2's go away and the L's go away, and what I'm left with is an integral I didn't have enough time to finish because time ran out. Right. We can crank that out pretty quick. So we'll crank that out, mention a couple more things. I want to finish up all the StatMech stuff today, not today, this week, because I want to start doing an energy landscapes on Monday. And then we can start seeing how all these ideas apply to a really fundamental idea of cooling. And then we can start seeing relaxation of what, from an energy landscape point of view, what relaxation is. We can start pulling a lot of really fundamental ideas. Plus, we're going to get some fundamental math. We're going to find out about diagonalizing symmetric matrices. Okay? And eigenfunctions and eigenvectors. Okay. Have a good day.
Okay. Yeah.